There we
wait,
go.
that makes more sense. Okay.
Okay,
You're actually.
so yesterday, physics sports fans, we worked through this, okay, which is just a fancy way of saying what? If you're in math class, this is a fancy way of saying what?
Slope and interval.
Y equals mx plus b, right? Now, on your equation sheet, and this is what you have to get through. So this is how it's written on your equation sheet, right? So don't flip out and go, oh my God, this is the only form in which I can use this equation, okay? No, you can solve this for acceleration, you can solve it for time, v naught, whatever. Okay, so one of the key things you've got to be able to do is use this equation. Well, remember, all this is saying is that on any velocity time graph, whether it's sloping down, whether it's negative going up, whatever, this acceleration is nothing more than the slope. This v is whatever your velocity is at some point in time. Your v naught is whatever your initial velocity is. Time is just on your x-axis. Okay, so that's all this is. This is just this is going to be important. All this is just a linear function. That's all it is. Now, yesterday we also came up and I showed you where this equation came from. X equals 1/2 at squared plus v naught time. Okay, came up with this. Now, we're going to do a little comparison and contrasting between these two equations, okay? And hopefully you'll see, oh, this is where this whole big idea comes from. So here's what we're going to do. So we're going to take the caret cart, okay? All right? And we're going to make it simple, and we're going to let the initial velocity be 0. Now, a lot of times what you'll see in these acceleration problems, not always, but a lot of times, either things will start at rest and accelerate, or they're moving and they accelerate to 0. Okay? So that isn't always true, but probably about 80% of the time on acceleration problems, either the initial velocity is 0 or the final velocity is 0. Okay? So don't flip out and go, oh, a car starts from rest. I don't know what the initial velocity is. Yes, you do. The car starts from rest. Okay? Or, I don't know what the final velocity is. The car is brought to a stop, okay? It's going to stop at 0. So, and you're not explicitly told that the initial velocity and the final velocity is 0, but you can figure that out. Now, so let's say that we're going to have an acceleration of, I don't know, 4 meters per second squared, okay? So is the car going to speed up? Yeah, it can't go much slower than 0, right? So here's what I want to figure out. I want to figure out at the end of 1 second, 2 seconds, 3 seconds, and 4 seconds, I want to figure out how fast the car is going at the end of each of these intervals. Okay? Fairly simple. So, and I want to show you a couple of different approaches you can take to this problem. I don't care how you understand this problem. Just understand the problem. So let's start with the velocity time graph. Okay? So, what's the velocity time graph going to look like? Katie. You kind of got the Princess Leia look with the hair up today. So, what's the velocity time graph going to look like?
It's going to start at 0.
It is going to start at 0.
It's just going to slope up.
International sign for a positive sloping line?
Yes.
Okay. All right, international sign for a positive sloping line. What's the value of the slope, Katie?
4 meters per second squared.
Yeah. So now I've got the slope of my line, 4 meters per second squared. Okay, well that's cool. So one way to figure this out, once you know this graph, is Miss McIntyre, at the end of 1 second, how fast am I going? Okay, this is the slope of the line. Pretend that you're in a math class, right? This is the slope of the line, which is 4 over 1, right? So if I go over 1, I'm going to go up 4. So at the end of 1 second, I'm going 4 meters per second. Okay, because that's what that acceleration means. Is that I'm starting at rest, and what I'm saying, and some people like to think of this way. This is 4 meters per second, if you want to think of it that way. So this is telling me for every second that goes by, this is how much my velocity changes. My acceleration is not how fast I'm going. It's the rate at which your velocity changes. Okay? So Ms. McIntyre, at the end of 2 seconds, how fast am I going? Beautiful. Then I'm going to be going 8. At the end of 3, I'm going to be at 12. And at the end of 4, I'm going to be going 16. Okay? So if you know the slope of the line and you're a linear kind of person, oh, I can do this. Okay? I can just look at the line and figure it out. Beautiful. If you like that, fantastic. Go with it. It's grand. So, but you're going, but Mr. Burkham, we've got the big dog equation sheet. We have equations. Let's use them. Grand. Okay? Let's use the equation. So, again, I know my velocity, I know my acceleration, and I know my values of time. So one thing I could do is say, oh, okay, well, this is simple. I got V equals V naught plus AT. What's my initial velocity?
0.
0. Now, you'll see me do this a lot. This is just like, this just says this goes away because it's 0. Okay, that's all that means. This thing is just going to 0. Now, so, because this goes to 0, what does that mean in terms of a graph? What is 0? Because this is 0. What on the line, what is 0? My y-intercept. Okay? Now, if the car was already moving at 2 meters per second, the line would start up here. Okay? But it starts at 0, so this just tells me my y-intercept is 0. That's all. So then you got, okay, well, that's 4 meters per second squared. All right, well, that's cool. So then I'm just going to plug in whatever value of time that I have. I plug in 1 second, I take 1 times 4, check my math, I get 4 meters per second. I plug in 2 seconds, I get 8. Plug in 3, I get 12. I plug in 4, I get 16. Pretty simple, right? Now here's what's important. When you have uniform acceleration, which you're always going to have, you're not going to have non-uniform acceleration. You're always going to have uniform acceleration. Here's the significance of this. Because it's acceleration just multiplied by time, it isn't time squared, it isn't time cubed, anything hinky like that, that just means that my change in velocity is a linear function of time. It means my velocity is changing the same amount each time interval. So this is why you have a straight sloping line on a velocity time graph. Okay? Now, we haven't talked about acceleration time graphs, but let's talk about acceleration time graphs for a second. What would an acceleration time graph look like? What would it do? Aubrey, what would an acceleration time graph look like? You're making this difficult.
It's the horizontal line.
A horizontal line at 4. So your acceleration time graph would be a horizontal line at 4 meters per second squared. Okay? So anytime you have uniform acceleration, it's a horizontal line on an acceleration time graph, which translates into a vertical line on a velocity time graph. Now, it might be sloping up, it might be sloping down. All I know is that it's going to be a linear function. Okay? Good so far. No worries. Now, let's figure out how far the car went. Now, could I do this? Okay? Think very carefully before you answer this. Read. I want to know how far the car has gone at the end of 1 second. Okay? So here's my question. You ready? Can I just take 4 meters per second times 1 second and say it went 4 meters? No? Yes. Those are basically your kind of options. Yeah. Yes. So I can just take 1 second, multiply that by 4 meters per second, and say I went 4 meters. You're good with this? Okay. Seems logical, right?
Oh, wait.
What?
It's a triangle. I'm overthinking.
I don't know. It is a
It is,
triangle,
yes,
so
it is.
what?
What is happening?
I'm completely overthinking.
How many think we can just take 1 second by 4 meters per second today is 4 meters? And
I
life is
feel like you
strange.
can't do it because that's too easy.
What? What?
No, it's gonna.
It's gotta be hard.
Wait, take 1
No.
second and divide. Wait, what was the question?
So I want to know how far it's gone at the end of 1 second. So here's my question. Can I just take 1 second and multiply it by 4 meters per second and say it went 4 meters? That's just the question.
No,
Oh, yeah. Yes.
Sydney, you say no.
no.
Mickey, why?
Because you're speeding up in that time. You're not going 4 meters per second the entire time.
Oh, when am I going 4 meters per second?
Exactly.
At exactly 1 second. Where do I start off at?
0.
0.
So do you want that?
Yeah.
Okay? Now, hold the thought, hold the thought, hold the thought. Okay, I'm going to draw this a little bit bigger. This calculation, usually when you're finding distance, has an identity crisis because there's a whole bunch of different ways that you can do this calculation. So here's what we know, is that we got a velocity time graph, which looks like this, and we said at the end of 1 second, we were traveling 4 meters per second. So if you like triangles, like, why I like triangles? I've always been a fan of triangles. Good, I'm happy for you. Okay? Some people like circles, some people like triangles. It's a personal preference.
I'm more of a square person.
I'm an octagon kind of guy, but that's just me. All right. So, because of the fact that this is not a rectangle, we have to treat it as a triangle, and we can go, oh, I recognize this. This is 1/2 base times height, right? So one option is that I can go 1/2 my base, which is 1 second, times my height, which is 4 meters per second, and I could get, wait for it, 2 meters. Oh, okay? It's an option. Okay, if you like this, beautiful. You can go with this, right? Now, but here's the downfall to this problem. Okay, here's the downfall. Huh?
I'll let you say.
Okay, what do you think the downfall is?
That if the acceleration changes,
No. Acceleration isn't going to change.
then I don't know.
What?
If it didn't start at 0.
No, it started at 0. That's a home run deal. Here's where this could potentially go south. You're using, I did not give you the 4 meters per second. Okay, you had to find the 4 meters per second. So if this 4 meters per second is wrong, this displacement is going to be wrong. Okay? So you always want to try and work off of known values as long as you can. You will reach a point where you have to use other values. Okay? But generally you want to work off known values as long as you can. But assuming that the 4 meters per second is right, that's cool. Now, yesterday we also came up with this little equation, that x equals v plus v naught over 2 times time, right? Okay? Or you can write it as 1/2 v plus v naught times time. It's the same idea, right? Now, look how this is similar. Notice that basically this is like an average velocity between the 2 points. Well, my final velocity is 4. My initial velocity was 0. So this becomes 0 plus 4, which is 4. Check my math. I divide that by 2, I get 2. I multiply that by 1 second, I still get 2 meters. So if you look at this with this 1/2, this is why this is like an area triangle. Because it's 1/2 base times height to a certain extent. But it's an average velocity multiplied by time. That's cool. Okay? If you like this equation, go, oh, my average velocity is going to be 2 because I'm going from 0 to 4. So the average between 0 and 4 is 2. I multiply that by 1 second. And you go, well, I like rectangles. All right, fine. So you would get the same idea if you made a rectangle that was 2 meters per second high. By 1 second, you'd still get a displacement of 2 meters. Okay? So it's like, why do I like rectangles? Oh, good. There's your rectangle. Okay, let's move on, Kenny. All right. Now, there's another option. Okay? And this is actually the preferred one. And that's x equals 1/2 at squared plus v naught time. Okay? Now, here's why this is a preferred one. Because I'm not basing this calculation off of a final velocity that I found earlier. This is all going off of known values. I was given my acceleration, I was given my times, boom, here you go. Now, what's my initial velocity? 0. So this whole thing drops out. I don't have any initial velocity, okay, which is cool, because that'll play out well. So, at this point, okay, as long as my acceleration doesn't change, which is not going to for now, right? So my acceleration was 4 meters per second squared, right? Times whatever time is going to be squared. Now, here's what's important, and this is why this ties into your math classes. If I take 1/2 of 4, I should get 2, right? So visualize this. I've got x equals 2 times t squared. Okay? This is how far I'm going to go. This is my time. Now, if you're in a math class, you would see this as x equals 2y squared. If you're in a math class and the teacher says, hey, graph this, what's this thing going to look like?
Parabola.
Something like this? Right?
Yeah.
You all have graphed that before, right? True? You've graphed this. You've graphed squared functions, right? Tell me you have.
Yes.
Yeah.
Okay, thank you very much. Okay, so here's where this turns into a bigger picture, okay? So, because of the fact that this is time squared, this is automatically going to take my position time graph and turn it into a quadratic function. So here's what's important. So I'm going to go with this, and if I put in 1 second, okay? So I'm going to kind of start over. I'm going to use this x equals 1/2 at squared plus v naught time. And here's going to be my position time graph. So I got 1 second, 2, 3, 4. So v naught 0 starts at rest. I don't have to worry about that whole thing. So I'm going to take 1/2 times 4 meters per second squared times 1 second, and then I'm going to square that. And lo and behold, miracle of miracles, I get 2 meters, okay? Which is what we got from the area of the triangle, okay? You can't have one set of equations saying, oh, it went 2 meters, and another set of equations going, oh, it went 3.5, okay? No, everything has to be consistent on how this deal was going to work. So, let's go, I don't know, 10, 20, 30, 40. So at the end of 1 second, I'm way down here at 2 meters. Okay? Now I'm going to put in 2 seconds. Now, would it make sense that if I went 2 meters in 1 second, that I went 4 meters in 2 seconds? Chandler, would that seem reasonable?
Yeah.
It would. So you think the answer is going to be 4 meters? Mm-hmm. No, it's not. Why? Because the seconds are squared. Okay? So, as soon as you see this being squared, it can't be a linear function. Anytime you see something squared or a square root function, it can't be linear. Okay? It can't be. So, if I take 2 and I square that, I get 4. 4 times basically 2 gives me 8 meters. So at the end of 2 seconds, I'm out here at 8 meters. Okay? 3 seconds, I'm going to take 1/2 of 4, and then I'm going to square that, 3 seconds squared. Okay? That gets me 9 times 2. That puts me out here at 18. And then my last one, I plug in 4. 4 squared is 16. 32. I'm way out here at 32 meters. Okay? So, oddly enough, my position time graph produces this nice quadratic function. Okay? because of the fact that it is time squared. Okay? So here's where everything now hopefully becomes a big idea. Okay? Now, I want you to think very carefully before you answer this next question. I'm going to come out here to this 1 second mark, and I'm going to draw a tangent line at the 1 second mark. Okay? Breckenridge, what's the slope of that tangent line at the 1 second mark? Beautiful. Why? You just get, sometimes a guess is good. Okay, Brecken, riddle me this. What does the slope of a position time graph give you? Velocity. How fast was it going at the end of 1 second? 4 meters per second. So at 1 second, if I come out here and draw that tangent line, it has to have a slope of 4 meters per second because that's how fast it was going at the end of 1 second. Okay? Now, well, it is, but that is my acceleration, but at the end of 1 second, if I start at 0, I'm going to be going 4 meters per second. Now, if I come out here at 2 seconds, and I draw that tangent line, what's the slope of that line going to be? 8, because that's how fast it was going at the end of 2 seconds. So notice what's happening as time goes by, what's happening to the slope of these tangent lines. They're continuously getting, because it's going faster. Okay? So here's the big picture. Okay? When you have uniform acceleration, okay? If you look at a position time graph, a velocity time graph, and an acceleration time graph. Okay? So in this case, I had an initial velocity of 0, and I had an acceleration of a positive 4 meters per second squared. So when I get this, that means my position time graph is going to be a curved line. My velocity time graph is going to be a straight sloping line, and my acceleration time graph is going to be a horizontal line. Okay? So all of these are showing the same thing. This is showing that I have uniform acceleration. It's shown by a velocity time graph because my velocity is changing the same amount in each time interval, and my position time graph is showing this because the slope is continuously changing. Okay? So now, if I change this and say, well, what if my acceleration had been negative 4 meters per second squared? Okay? What if my acceleration had been negative? How would all three graphs change? Well, first off, I'm going to have zeros. Okay? So let's start with my acceleration graph. What would my acceleration? What's the only thing that would change on my acceleration time graph? Yeah, it's still going to be a horizontal line, but it would be down at negative 4 meters per second squared. What would my velocity time graph look like? Instead of sloping up, it's going to slope down. Okay? But with a slope of negative 4 meters per second squared, what's my position time graph going to look like? It's just going to get flipped over, and it's going to go like that. Yeah, again, I'm not. The time isn't what's negative. It's the constant in front of it. Okay. All right. So, anytime you have uniform acceleration, acceleration time is horizontal. Velocity time graph is going to be linear. Position time graph is going to be some quadratic function. Got it? Good? Grant? Beautiful. Okay. So, how you can use this. So let's talk about this equation, 1/2 at squared plus v naught time. Okay? So acceleration is really tough to physically measure. Velocity is somewhat easy. Acceleration is tough to measure because you have to have a rate at which it changes. So here's what I want to do. So, turn that over a little bit. And stop if that works. Okay? You're going to time this.
All right.
Got it?
Oh,
So here's what we're going to do. I'm going to turn on the fan cart.
Maybe.
Maybe. Okay? So I'm going to turn on the fan cart. Now, what's the initial velocity of the cart?
0.
0. Okay? And again, just like we did earlier, I'm going to have the fan run up to full speed. So when I look at that equation, I have x equals 1/2 ac squared plus v naught time. I'm going to start it at 0, so I don't have to worry about this part of it. So what can I measure? I can measure time.
distance.
I can measure how far it's going to travel. So I want you to stop this when the back wheels cross the 1 meter mark. Okay? So we're going to know how far it goes, and we're going to know the time. And the initial velocity is going to be 0. So, okay, you ready? 3, 2, 1, go. Stop. So what'd you get?
3.06.
Okay, 3.06 seconds. So, I know my distance was exactly 1 meter, right? I measured my time. The only thing I don't have is
Acceleration.
acceleration. So then I can sit there and go, okay, how can it get acceleration by itself? Matt,
Over.
I need to get acceleration by itself. What can I do? No, I hate fractions. Get rid of the fraction.
Yeah.
Multiply by 2. So that gives me 2x, then what? Here.
Oh.
Sorry.
It's
Gotta catch
okay.
up on the camera. So I multiplied by 2, I got 2x, now what? So now I'm going to get time squared over here. Beautiful. So then I'm going to divide by time squared. That it?
Yeah, pretty much.
So, yeah, because the a is just by itself. The a isn't squared. Okay? So, boom, there we go, right? Good? So, now, so in this case, I'm going to take 2 times 1 meter, and then I'm going to divide that by my time squared. What was the time? 3.06 seconds squared. Now, here's the big question. What units should I get? Do I get meters per second squared?
Yes.
Yes, how cool is this? Okay? So, somebody do the numbers. Basically, somebody take 2 and divide it by 3.06 squared. It's going to be a pretty small number.
Oh. Uh, 0.21.
0.21
Yeah.
meters per second squared. Not a very fast acceleration. Remember, if I drop something, that's like 9.8 meters per second squared. So, this is a fairly slow acceleration. Okay? All right? Well, that's cool. Now, let's look what we can do with just this idea. So, what's the velocity time graph going to look like for the cart? Miss Hillman, what's my velocity time graph going to look like? Boom, like this. Okay? What's the slope of the line? Yeah. So the slope of the line is 0.21 meters per second squared. Now, could I find the final velocity of the cart?
Yes.
Do I know the time? The time was, what, 3.06? So, how can I figure out how fast the cart is going at the end of that time? Yeah. So I know V equals V naught plus AT, right? Do I know the initial velocity of the cart?
Mm-hmm.
Do I know my acceleration?
Mm-hmm.
Do I know my time?
Mm-hmm.
Yeah. So somebody take that acceleration of 0.21 meters per second squared and multiply that by 3.06 seconds. What'd you get?
0.64.
0.64
Yeah.
meters per second. Okay? Not very fast, right? Okay, well that's cool. All right. Now, how does the the 1 meter play into this velocity time graph?
The displacement
Which would be the,
area of the
yeah. So if I were to find the area underneath this graph, it has to have a value of what? 1 meter. Because that's how far it went. Okay? So these are how all these things interrelate with each other. Now, we have one last equation to do. And it's on your sheet. And that's that v squared equals v naught squared plus 2a x minus x naught. Now, this equation we will eventually derive, but it comes from the idea of conservation of potential and kinetic energy. So for now, just accept that this equation exists. Okay? But it's a beautiful equation, and I'll show you why. Let's look at what we know so far. We know we had v equals v naught plus at. We had x equals 1/2 at squared plus v naught time. And then the one that we also had was v plus v naught over 2 times time. So here's the $1 million question. And over the years, this has become known as that equation. Okay? If you know Nettie from last year, Nettie named this that equation. So this is literally called, it's just stuck. Oh, that equation. This is this topic. So what's the difference between that equation and every other equation? Oh no, there's a fundamental difference. Well,
There's a initial.
no, no. What's missing from that equation that's in everything else? Time. If you ever get any problem that doesn't involve time, go to that equation. This is the only one that's not dependent upon time. Okay? This is the only one. So you all tend to freak out and you want to go, oh, my God, I got to have time. No, you don't. Okay? If you ever come across a problem that does not involve time, immediately think of this equation. Okay? Immediately think of this equation. Because you, for whatever reason, and I'll show you how this works in just a second, you all want to try and find a time, then use these equations, and you go through a god-awful amount of work, and it's probably wrong anyway. So just go with this. So here's how this would work out. So let's say that you've got a world-famous Carrot car, right?
Mm-hmm.
And let's say that it's moving at, I don't know, 10 meters per second, right? And I want to bring the car to a stop, or let's just say I want to slow it down to 2 meters per second, okay? So imagine this. You're looking at this car, you know that you're moving at 10 meters per second. You slow down to 2 meters per second, so you're going from 10 to 2. And let's say that you measure that distance while this is happening, okay? And you realize that you measured that and it's 12 meters, okay? So I want to know what's the acceleration of the car. Now, before you do anything else, okay, let's think this through. What's the car doing, speeding up or slowing down?
Slowing down.
Slowing down. So what sign should my acceleration have? Negative. Because I have positive velocity and I'm slowing down, so I should have negative acceleration, right? So even though you don't have to, look at this on a velocity time graph. You're starting at 10 meters per second, and you're ending up down here at 2 meters per second, right? But here's the deal. Did I tell you the time? No. But how does the 12 meters relate to this graph? Yeah, that's the area, but I don't, since I don't have the base of the triangle, I can't really work this as an area because I don't know what the base is, and I know what this part is, but I don't know what the base is, so I'm kind of screwed that way. So you're sitting there going, wow, I don't know what to do. Could I do this? I really wanted time. I like time, Mr. Rookie. I'm a big fan of time. Could I take and do this? Could I take, well, if I take 12 meters and divide that by 10 meters per second, the meters cancel out and I get 1.2 seconds. So it should take 1.2 seconds for this to happen.
No.
It's not at constant velocity. If you ever find yourself doing this on this assignment today, stop. Don't. Okay? Don't. Do not do that. Okay? Do not do that. So at this point, you're going, wow, I got an acceleration. I'm trying to find. I know initial velocity and on final velocity, I know distance, but I don't know time. So right away, what are you going to use? That equation. Okay. So I got v squared equals v naught squared plus 2ax. Right? I know everything except acceleration. So how am I going to get acceleration by itself?
Stop.
What's the first thing I'm going to do? So I'm going to have v squared minus v naught squared. Okay, that's cool. Now what? Divide by
2a.
2x is going to equal
2x.
my acceleration. Cool? Solve these equations first. Don't put in the numbers. Solve the equations first. Okay. Now, at this point, now we can start to put in some numbers. Okay? So, I've got v. Now, is the v going to be my final velocity or my initial velocity? Final. Well, in this case, my final is going to be 2 meters per second. And that's going to get squared. Minus my initial velocity, which is 10 meters per second. And that's going to get squared. And then I'm going to divide that by 2 times 12 meters. Now, here's what you're going to do wrong. You'll flip these around. You'll put the 10 here and the 2 there. But if you do that, here's the deal. Then you're going to get a positive acceleration, which right away conflicts with the idea that you're slowing down. Okay? So that's why it's a good idea to stop, look, and go, okay, hey, what's going to be happening here? So, somebody do the math. Take basically 4 minus 100, which is 96. 96 divided by 24.
-4.
-4?
Mhm.
I'd like to say I had that planned and it worked out that way. -4 meters per second squared. Does that match with what we said was going to happen?
Yes.
Yes. Okay? Right? It matches. Okay. Now, how much time is going to elapse, by the way?
Well,
Well, look, this is my acceleration, -4, right? So if I start at 10, 1 second later, how fast am I going?
6.
6? Right? Because this is what this means. Every second that goes by, my velocity drops 4 meters per second. So at the end of 1 second, I'm going 6. At the end of the second, I would be going 2. So it would take exactly 2 seconds. Okay? Now, one of the things I'm going to ask you to do a lot is draw velocity and acceleration diagrams. So if I said, hey, draw velocity and acceleration diagrams for this, it's what you did on the lab that I just gave back when the cart was going up the hill. So if I said, hey, draw what's happening, here's what I would want. Here's the wheels, here's the car. Initially, and I don't care what the numbers are, all I'm trying to do is showing what's going to happen. So I'm going to start with some positive velocity. I'm going to call this V1. I really don't care what the numbers are. I just want to know what's going to happen. So as this car moves along, what's going to happen to this vector? It's either going to get bigger or it's going to get smaller. It's going to get smaller, right? So maybe have this as V2, maybe have this as V3. Now, which direction is my acceleration vector pointing? It's either in the same direction or it's in the opposite direction. Opposite, because that's what's making it slow down. So just come up here and go, okay, now, as it goes, what happens to my acceleration vector? It stays the same because that's the same slope on the velocity time graph. Oh, how cool is this?
Magic.
Magic. Or physics, whatever, it's the same.
Magic.
Okay, so if I say draw a velocity and acceleration graph for a situation like this is what I'm looking for. So basically, all these velocity and acceleration graphs will play out one of two ways. Either you're going to slow down and the vectors are going to get smaller and the acceleration vector points in the opposite direction, or it's going to speed up like this and the acceleration vector is going to point in the same direction. So either make your acceleration vectors point in the same direction or make them point in the opposite direction. Okay, stop that, camera. Okay, now, on this assignment, and all assignments that you will have like this, and you will have a lot like them, okay? Here's how I want this done. In a very, very specific way I want this done. These are going to be done on your sheet of notebook paper. So here's your sheet of notebook paper. Now, some people take this to an extreme. I really don't care. But imagine that there's a line. Some people just imagine the line. Some people will actually draw the line about 2 inches in. The only thing that exists in this column right here are the answers. That is it. Okay? Only the answers go here. The work that generates them go over here. Okay? So I don't want this all blended into one thing where I have to try and sort through your paper to try and figure out what you've done. And they'll go, oh, I put a box around the answer. Okay, I'm going to put a box around the 0 that I'm going to put on the top of your paper. Okay? This is how I want it done. It makes it easier for me, and it makes it easier for you. So if you'll notice, on the first 6 questions, those are all multiple choice. I want them answered on this sheet. Okay? So you're going to go 1, 2, 3, 4, 5, 6. If there happens to be some work over here, put some work over here. But here's what I want the answers to the 6 multiple choice questions. Don't circle them on there and expect me to flip back and forth between the 2 pages. Okay? Now, when you get to number 7, it says, can an object move with uniform acceleration and constant velocity at the same time? So number 7, if it's something where you have to write out, okay, you can write it out and go across like this, and okay, here's your answer. Okay, well that's cool, because it's something that you have to write out. When you get to question number 8, okay, and I'm going to work number 8 exactly how I want number 8 worked, okay? So, you got a rocket lifts off its launch pad and travels straight up, attaining a speed of 100 meters per second in 10 seconds, calculate its acceleration. So I'm going to go, okay, here's number 8. So the only thing I'm going to put beside number 8 is my eventual answer. This is what I would recommend. Write down what you know. If you read number 8, what information did I give you? What's one thing I gave you? Which velocity? So my final velocity is going to be what? 100 meters per second. What else do I know? I know a time of 10 seconds. What else do I know?
Traveling straight up.
Yeah, but that's on something really variable.
It's lifting off its launch pad.
So what's my initial velocity? 0. So V naught is going to equal 0. What am I trying to find? My acceleration. Okay, so imagine you run. So I need my acceleration, right? So you might come over here and go, okay, well, here's my rocket, right? Okay, so we start here, it's going to go straight up, okay? If nothing else, draw a picture. So here's what I need to do. I need to choose an equation that relates velocity, velocity final, time, and acceleration. So what of the equations relates those variables? V equals V naught plus AT. So what's the only thing I don't know? Acceleration. So I got to get acceleration by itself. So that's going to be V minus V naught over 2. Is going to give me my acceleration. Okay? Now, the last thing you do is put in the numbers. That is the absolute last thing that you do. Now, is my acceleration going to be a positive or negative number? Because I'm speeding up with positive velocity. So I'm going to take 100 meters per second minus 0 divided by 10 seconds, and I'm going to get
10.
10 meters per second squared. Okay? Now, when you do number 9, leave a space between 8 and 9 because I don't want this work being all blended together. I want to be able to distinctly see the work separated between number 8 and number 9. Some people will actually like shade in a line in between. You don't have to do that. That's kind of extreme, but some people will do that. Some people actually do like little designs in there. Okay? Whatever. Okay? But the main thing being is that I want the work that goes with number 9 beside number 9. Here's what I don't want. I don't want you to put, oh, here's number 8, 9, and 10, and then draw an arrow and go, oh, here's the work for number 10, oh, here's the work for number 9. I will go to levels of being irate that you have never seen me before. Okay? Don't. You want to keep this organized. You want to keep, okay, here it is, life's good. Now, let me give you a hint. When you get to question number 17, okay, so let's talk about 17. So, a driver traveling at 20 kilometers per hour abruptly stops the car at 3 meters. Later, while moving at 40 kilometers per hour, the driver uses the same acceleration. Draw motion diagrams. What's the value of the acceleration? How far will it travel? So here's the deal. What is missing from 17? What variable is missing? Time. Okay? There is no time in 17. So what equation are you going to use?
That one.
That equation. Okay? Now, you have 20 kilometers per hour. Okay? What are you going to do with the 20 kilometers per hour? Convert it into meters per second. Do not leave that in kilometers per hour. Multiply by 10, divide by 36. When you do something like that, keep a lot of digits in the meters per second. Don't round that. Okay? When you're doing a subcalculation and a conversion, you want to keep a lot of digits happening in that conversion. So, you're going to do a whole bunch of things on 17. You're going to draw a motion diagram. Okay? So you're going to say, okay, here's the car, it's moving. What's going to happen to the velocity vectors? Are they going to be getting bigger or are they going to be getting smaller? Which direction is the acceleration vector going to point? In the same direction or the opposite direction? Those are things that you want to think through. Okay. I'm done. You're on your own.